Okay, I think we'll go ahead and get started. We're just about a minute past 11 Eastern Standard Time and 10 a.m. Central Standard Time. So welcome, everyone. My name is Trevor King. I'm over the marketing and business development for StarChem. If you don't know, StarChem, we are a specialty chemical manufacturer based in Spartanburg area of South Carolina, located really in between Greenville, actually between Charlotte, North Carolina, and Atlanta, Georgia, just off 85, if you know the area. Our manufacturing site has been there for quite some time, for about 60 years. We've manufactured under different names and different ownership. In the past, we were known as Tanatex, and then after that, Bayer and Lanxess, but we've been StarChem since 2007. We manufacture a lot of different chemistries. What we're going to talk about today is a lot of our derivatives off tertiary amines. So we make a lot of amine oxides and quaternary ammonium compounds, and due to the current state of the economy and the things that are going on, it's really impacted supply. And so we want to talk a little bit about that, educate everyone on where we are, some of the alternative products that we're looking at and we offer in place of the materials that are hard to get. And just to let you know, we're recording this and we'll post this into our booth on the ISSA Show website, so it can be accessed and watched later. But as we get going, I'll introduce Bjorn Hanser, who is our business director in Canada, and Gail Fortin, who's also a sales manager and business development in Canada. They're both very very well integrated into this issue and are very active in our business, and kind of led us in this area of HI&I. And I'm going to let them take over the presentation and discuss with you some of the supply chain situations right now, then obviously the technical aspect of what we're doing to try to help alleviate some of the issues with supply of these raw materials. So Bjorn, I'll let you.
Okay. Thanks, Trevor. Appreciate it. So, as Trevor mentioned, there's a lot of changes in the market depending on certain raw materials, and we cover those in this presentation, mainly the impact of tertiary amines and especially the dimethylamines. There's a heavy impact on tertiary amines on market pricing, on availability, and so on, and we cover this in the next few slides. So obviously, COVID-19, the coronavirus has impacted all industries worldwide and in different ways. So now we've been impacted in various markets, negatively, like oil and gas, like automotive, textile, and so on. These markets are really went down, while other markets like personal care and HI&I, so home care and institutional industrial cleaning market, has been increasing significantly. So it's good and bad from a business side for us. Now, what we've seen is a big issue for us is getting enough raw material supply for certain surfactants we manufacture, which are core ingredients in HI&I formulations. And what happens is, due to the pandemic, there's a significant increased global demand for cleaners, for disinfectant and sanitation products, which are formulated using a very certain type of surfactants, such as amine oxide, benzalkonium chlorides, and other surfactants, and they are made by reacting tertiary amines, and especially dimethylamines. So we're seeing a huge demand, and which takes away raw material supply, and we really see it shortening, and we see allocation. So we are on allocation. A lot of our competition are on allocation, and simply we cannot get enough raw material to fulfill our customers' demands. So what happened is we have three slides about this. So you will see an increased volume requirements all over the world from the existing customers, and then you see further reduction of raw material, which will be based on in Q1, for example, one of the major suppliers Trevor, just the screen went black. I don't know if... Yeah, that's back. Okay. So further reduction of raw material availability. What happens is one of the major supplier, Eastman, will shut down the plant in Europe in Q1 for 2 months. Now, even though that's Europe, but the Eastman US plant has to support Europe. So there will be a significant drop in availability of raw material in Q1. What we also see is that a lot of raw material stay in Asia. So usually Asia is a big exporter of raw materials, tertiary amines, into other regions, but they need those raw materials themselves. Third, what we see is we see a high demand of new customers, customers from other markets like oil field, like automotive. They suddenly make hand sanitizers, they make cleaners. So a lot of interest from new customers who've never used those surfactants before are now wanting to buy them. And we see there's a little bit light at the end of the tunnel. In Q2, 2021, we expect more feedstock availability. A, the shutdown of Eastman will be done, but B, there will be two new suppliers coming online, one in Singapore and one in India. And so there will be more raw material available in Q2 2021. Now, to what that effect will have on the market, we will see. But it's a bit too early to predict. But we expect it to be more raw material availability and a little bit less cost pressure. So Trevor, next slide. So this is what I said. So what we see is a huge increase with existing business, existing customers within the existing market. Now this is from the Business Wire report. The link is underneath. So it's just a simple graph which shows you how significantly the growth rate is for the hard surface disinfectant market. So if you look on the growth rate from 2019 to 2024, it nearly doubles in demand. So we see that we have some of our key customers like global multinational accounts. They forecasted a 30 to 40% increase in the demand for next year compared to this year. And this year has been already a strong year for them. So we see significant demand. I mean, everybody's disinfecting everything, restaurants, malls, churches, I mean, at home. So this is a significant increase in demand of the existing customer base. Yeah, and another important thing is you see 63% of the global growth will actually be in North America, so the US, Canada, and parts of Mexico and Latam. So there's a big increase in our region, and the key driver is really the pandemic, and it's called the HAI, which is a healthcare associated infection number. If that increases, this market will increase, and it will stay like that for a longer time than just a few months. Next slide, Trevor. So this is the second one. So what we see is that how does it impact, let's say, the core markets using those surfactants is HI&I and personal care. And these are the two, this is out of a questionnaire from the Happy magazine, and the link is underneath. So what we see is that they have done a survey with HI&I company and personal care companies. Is it impacting your sales, the pandemic? And yes, 75% of HI&I companies says yes, it impacts our sales. Obviously, they sell more. 25% say no. Depends, of course, what area you're into. Now, increase in interest for antibacterial product for personal care is 80% growth. So again, now if you look at those industries, they're using already those raw materials, and they see around 75 to 80% increase interest. So they need more of these raw materials. Next slide. And now I hand over to Gail, which is, Gail is an expert. She worked 25 years in R&D and has worked with amino oxide pretty much all her professional life. And she will guide us through the amino oxides which are impacted by the dimethylamine shortage. And she will take us to some alternatives we have to offer which are not impacted by this. So I hand over to Gail.
Okay, thank you, Bjorn. Okay, so building on what Bjorn has just shared regarding dimethylamine supply being tight, increasing costs, I'm going to review some of StarChem's key amino oxides and compare performance characteristics of those that are affected by this dimethylamine supply issue to those that are not affected by this issue. So the intent here is to provide formulators with some very basic information so that they can decide if considering an alternative amino oxide, one not affected by the current dimethylamine supply issues, is an option in their current formulations. So that's the intent of what the information I'm going to go through today. Next slide, Trevor. Okay, so first off, some basic amino oxide characteristics and uses. Primary, secondary surfactants in a formulation. We're seeing it traditionally. It started off more secondary surfactant. We're seeing it used more and more as a primary. It's an amphoteric. It's compatible with cationic, anionic, and non-ionic surfactants. So a lot of flexibility formulating. Now, these next two are the key characteristics that I'm focusing on today in this presentation, and that's the foam stabilizer, foam booster characteristic, and viscosity modifier. So these are very key performance characteristics for amino oxide. This is why they're added in a lot of formulations, and that's what I'm going to focus on later on. They're sulfate-free, they're mild co-surfactants, good detergency, biodegradable, and good wetting agents. Not affected by water hardness. They function as emulsifiers and can be anti-static. And then just a little note at the bottom, the lower pH, the amino oxides tend to behave like a cationic, and the higher pH in a formulation, the amino oxide will function as a non-ionic. Okay, so now next slide, Trevor. Okay, so here we're looking at the four amino oxides, the four main amino oxides that StarChem produces. So on the left-hand side, we've got lauramine oxide, our StarSurf LOX, and we have myristyl amino oxide, our StarSurf MOX 1480. Now, these two on the right side are the ones that are in tight supply related to the dimethylamine supply issues that Bjorn had talked about. StarChem sources the tertiary amine, so the dimethylamine, whether it's the lauryl or the myristyl, we purchase those. So we are, involved or tied to that those constraints in supply right now. Now, if you look at the two surfactants on the right side of this page, these are the two that are not affected by the dimethylamine supply issues. So this is cocamidopropyl amino oxide, StarSurf CAPOX or CAPOX, and the lauryl myristyl imidopropyl amino oxide, our StarSurf LMAPOX, or LMAPOX is referred to as well. So these two on the right-hand side, StarChem actually manufactures the tertiary amine, so we're not constrained by the supply issues on the other two. So looking on the left side, we've got two products that we manufacture, lots and lots. Anybody making amino oxides is probably making one or both of these two. And on the other side, we've got two potential alternatives that are not in tight supply, that are very stable supply right now. So left versus right, very similar functionality in some of these, in comparing some of these amino oxides, the left side versus the right side. So we decided to investigate how similar they were and give formulations or formulators possible alternative to use, formulators that may be heavily tied to lauramine oxide, for example. If we can offer them data that gives them the ability to potentially switch to StarSurf LMAPOX, that will give them a cost advantage and also more availability. So that was the intent. Let's look at how similar these functionalities are and see what we can offer. So the next slide, Trevor. So before I go into the actual performance characteristics of these 4 amine oxides. I wanted to talk briefly about bleach stability. So we know that loramine oxide, myristylamine oxide are stable in hypochlorite bleach. All 4 of these are stable in hydrogen peroxide bleach. We wanted to investigate stability of the potential alternatives in hypochlorite bleach. So we did a bleach stability test, ran it for 30 days. And here we see the data looking at the loramine oxide, the myristylamine oxide, and the CaPOX and the LMAPOX. So we did a 30-day stability study, 8% bleach solution and 2% amine oxide, and we monitored pH, color, and appearance. So you see the day 1, the start, the results there, and day 30. So, and it basically confirmed what we already knew, but I wanted to share the data so it was very clear. So LOX, MOX 1480, very stable in hypochlorite bleach. The CaPOX and the LMAPOX, not so stable. They failed very early on. We monitored it for 30 days and it got worse and worse, but they failed at day 2, both of them. So not recommended for using these 2 possible alternatives in hypochlorite bleach formulations. But again, to highlight the fact that all the amine oxides are hydrogen peroxide bleach stable. It's part of their manufacturing process, so they are stable in hydrogen peroxide bleach. So now moving on to the 2 characteristics that I wanted to focus on as far as providing some data to decide whether or not looking at alternatives is going to be suitable or ideal for various formulations. We first are looking at the viscosity profile. So basically what we did here is we took a very, very basic cleaner formulation. So sodium neutralized dodecylbenzene sulfonate, DDBSA, and then sodium lauryl sulfate, and the test amine oxide. Very basic formulation. And then we did a simple viscosity profile, salt curve on each of these formulations. And if you look at the graph on the right, if you look at the blue and the red lines, those represent the myristylamine oxide and the loramine oxide viscosity profile curves of this very, very basic formulation. Now, I know the myristylamine oxide looks a little wonky. My intent here was to get all the data represented on one graph. And myristylamine oxide builds very, very high viscosity, and I just wanted to highlight here, while the LOX, the CaPOX, and the LMAPOX all peaked at around 3,500, 4,000 CPS. The myristylamine oxide formulation peaked at 30,000 CPS. So that's why I just wanted to show that it was way off the scale, but I wanted to keep the scale as such so that it was easier to understand the graph. So in conclusion, as far as viscosity, using LMAPOX or CaPOX in place of LOX or loramine oxide should provide a similar viscosity. There may be some adjustments necessary. You may have to adjust the amount of salt added, may have to play around with active ratios in your formulation, but you should be able to get to a similar viscosity by replacing your loramine oxide with one of these alternatives. Again, with some tweaking likely. And it's obvious from the graph that it's likely going to be a challenge to meet the viscosity profile of MOX with either of these alternatives that we're offering here. If viscosity, very high viscosity, is a main function in your MOX, your myristylamine amine oxide based formulation, it's going to be really hard to meet with an alternative amine oxide if viscosity is your main factor. Not to say that it's not doable, but it's likely going to be quite a challenge. So viscosity wise, for the LOX anyway, the two alternatives we're offering potentially a suitable alternative. Something to keep in mind here is that this is really just presented as a guideline. There's a lot of factors that can affect this graph, a lot of factors that can affect the viscosity profile of your formulation. Switching out the primary surfactant package instead of DDBSA, using sodium lauryl ether sulfate instead of SLS, if you switch out ammonium lauryl sulfate. These are all factors that can change that viscosity profile significantly. Fragrance, pH range, these are all things that can affect your viscosity profile. So it's recommended, if this is just some basic information, guideline, suggested you get some samples and obviously work in the lab and do some preliminary work up front before you would consider an alternative. Trevor, next slide. So now moving on to the other main characteristic, performance characteristic, we're looking at foam stability. So what we did in this case was the samples, the formulated samples that we prepared for the viscosity profile evaluation, we performed the cylinder shake foam tests with each of those samples. Now I haven't put all the graphs on here, but I put the two main graphs because in a cleaner formulation, you typically would have either no salt or very little salt, not often more than 0.5%. In some cases, yes, but generally the salt concentration is relatively low. But there's some interesting information in this graph. So looking at an alternative, the conclusion based on the foam, if you look at the top graph here, the LMA-POX is a very similar flash foam to both the LOX and the MOX. So if you look at the bar graph here, the blue represents the initial foam, and the red bar represents 4 minutes later, the same measurements. So it's showing flash foam versus foam stability across the board for each 4 of those surfactants. And this is based on that formulation you see on the left-hand side. So again, LMA-POX looks like it would be potentially, if foam is an important characteristic, LMA-POX could be a potential alternative to either lauryl or the myristoylamine oxides. CAPOX, the CaPOX, is showed lower in the foam height. Sometimes that's desired in a amine oxide-based formulation. Sometimes foam needs to be stronger. So so based on the samples we tested with no salt, you can see the results there. Now, what was interesting, thank you. What was interesting is that the tests we did with containing 0.5% sodium chloride, the CaPOX and the LMA-POX both showed a better flash foam than either the lauryl or the myristoylamine oxide in the presence of sodium chloride. Now, this is exactly the same test formulation you see up there in the left-hand top, just with 0.5% sodium chloride. The only difference between those 4 different bar graphs is the amine oxide used. So very interesting result here, incorporating a little bit of sodium chloride could have some advantages on your foam height characteristics. So I think we can go on to the next slide there, Trevor. Okay, so this really is essentially a list of the parameters that you find on our certificates of analysis for the 4 StarChem amine oxides that are listed here. The 2 primary ones that are affected by the supply issues, the LOX and the MOX 1480, and then the 2 potential alternatives not affected by the supply issues. And you just see the list of parameters that are listed there. All of the amine oxides are considered self-preserving, so there's none added in any of the 4 amine oxides you see listed there. So that's just some basic information. And then I guess in summary, due to the tight dimethylamine supply, some amine oxides such as lauramine oxide or myristoylamine oxide are suffering shortages, allocations, and increased costs. So when or if LMA-POX or CaPOX can be substituted, they can provide a more cost-effective option with a stable supply chain. So all in that, I hope that the data we've provided is helpful in investigating whether or not substitution is an option for your loramine or myristoylamine oxide-based formulations. And the next slide is simply a thank you for listening. Thank you for joining our presentation today. Again, we hope you found the information useful, and just hit our booth if you've got any further questions or would like any additional information. Trevor, I'll let you wrap things up.
Yeah. Again, I appreciate everyone for joining us for this webinar. Certainly, if you've got any questions, let us know. You can hit the Q&A. You can also go to our booth and hit any of our contacts and chat with us. Our contact information is there. You can also call us or email us. I will upload this presentation is already uploaded to our booth, but I'm going to also upload the video from this webinar as well later today. But again, we appreciate your participation. Are there any questions anyone has? Well, if not, again, I appreciate it, and everyone have a great rest of your afternoon and a very safe day, and keep safe, and look forward to talking to you in the future. Thank you.
Thank you.
Thank you.
Thank you.